Hello, everyone. Thanks for coming to our talk. As you can see, Loose Lips Multipliers. This is a project Kyle and I have been working on for a little while. So I'm Mitch Kidder. I'm the Director for Security Architecture and Planning at GCI.
And my name is Kyle Easterly. I'm the Chief Technology Officer at Pango Technology.
Both of us are based here in Anchorage. We originally presented this talk at DEF CON in the AI Village earlier this year. It was about a 20-minute presentation. Matt and team were kind enough to give us up to an hour of time to talk today. We ended up revamping the presentation to make it more suited to this audience, but included all the same great nuggets that we had at the DEF CON talk. We'll be talking about generative AI basics, large language models. Then we're going to talk about our research objective and methodology, the things that got Kyle and I interested in this topic, and how we went about researching this effort. Next, we'll walk through how we created a specific data set for this research, and then how we went into the model training. Then we'll show you something called a model inversion attack and teach you a little bit more about that. And then finally, we'll wrap up with some takeaways, things that we hope you'll take home back to your organizations that you'll be able to leverage.
All right, so we're going to cover briefly the history of AI. It seems like it came out of left field this year. ChatGPT came out, everyone started using it around the office and at home and everything, but it's actually the result of decades of work. So artificial intelligence really began as a field of study in the 1950s. Been working on that for a long time. Essentially, we've been trying to get computers to think as long as we've had computers. In the 1990s, machine learning really took off, and this is where we switched from writing down a large number of if statements to actually showing the computer examples of data and getting it to build a predictive model from that data. You use this all the time. It's in social media algorithms, it's in cybersecurity tools that do detection, and so on. And then in the 2010s, everybody figured out you can use these things called GPUs to do massively parallel data processing, and that allowed us to take some of the inner workings of the machine learning models and stack them into layers, and that's why it's called deep learning. And that allows you to do much more potent things like self-driving cars, early image recognition and whatnot was built on that. And then at the end of the 2010s, we had Attention Is All You Need and some other breakthroughs in research that gave us generative AI, which shifts AI from a predictive tool into something that can be used to generate new content similar to what it's seen. You commonly guide this with input that we refer to as a prompt, so you'll hear the word prompt a lot in the rest of the talk. And you commonly see this in tools that folks probably already use, ChatGPT, Midjourney, and so on. Knowing the history makes charts like this make a little bit more sense. The breakthroughs that are happening towards the end of the 2010s, not necessarily out of left field, right? It's decades of research that's been building and compounding on itself, and then we finally figured out a couple of cool things you can do with hardware to parallelize and really step up the training on these things.
And Cal, can you describe some of the labels on there?
Yeah, oh yeah, it's a little blurry. So we've got handwriting recognition as the red line. Speech recognition took a while. We had to get into deep learning to do that very well. And then reading comprehension and language understanding, which is mostly what we're going to be talking about. Those really no one really even tried until we had deep learning. And now you'll notice the chart cuts off in 2020, so you might be wondering where are those lines now, right? So we're roughly here. We're all the way off the edge of the chart. And an example of what you can do now is now we're combining those capabilities. So the chart showed image recognition and language understanding separately. And right now, for $20 a month, you can download the ChatGPT app on your phone and send it a picture of a joke and have it explain what's going on and why it's funny. So we've got our lightning cable disguised as VGA, and that's funny to nerds. That's kind of AI in general and how we got here. We're going to talk a little bit about the inner workings of large language models and how those things actually function. So this sentence here, can anybody tell me, just raise your hand, what's probably the word that goes at the end of that? I heard right, yep. Okay, why did you say right? So most people, when I ask this, will say, well, I looked at the word left. So didn't turn left, turn right. Also, when I ask a lot of folks, they don't necessarily say this right away, but we're also paying attention to the word instead. And this is what the Attention Is All You Need paper really gave us, is the ability to consider all of the input from a massive amount of input text and then decide what's in that last position. Now, these language models don't just tell you the top most likely word that's going to be in that spot. If you have control over the model and you're running it on your own infrastructure, you can actually see the probabilities for all of the words the model knows in that position. So maybe around could be in there, but it's not the top scoring thing. It's not the most obvious. Maybe back is in there. Maybe sharply right. There might be modifier words that come out. So if you have something running locally, you can look at this. This is not something you can really do with ChatGPT. It's just going to tell you the top most likely thing that it's been trained on. Now, because of this next word prediction, this allows us to use these things for useful tasks. So if you can set something up as a next word prediction problem like we have here, it'll tell you the capital of France is Paris. You can use it to generate code. You can use it to summarize text, ask questions about text, and all sorts of other tasks just by shaping the input a certain way. Now, how these things know how to do all of this and how they know so much about language understanding is the scale of the data sets they're trained on. So we're going to show you this with a little visible demo. So in a human lifetime, you're going to speak about 1 billion words. And on the scale that we're going to show you today, that is 2/100ths of 1 inch. So I'm not even going to open this. So that's how many words you're going to speak. You might read about 7 billion words in your lifetime, which is, I'm also not going to open it, that is 1/10 of an inch on the scale. GPT-3, which is what really kicked all of this off and what ChatGPT launched with, is 300 billion words, which is about 6 feet. And in June, Meta released an open source model called Llama 2 that's trained on 1.5 trillion words, which is 30 feet on our scale. So if you compare that to the amount of words you can possibly read in a human lifetime, it's just staggeringly impossible for a human to catch up to that. Now there's another metric that you'll see thrown around a lot, and that's a parameter count. How many parameters does it have? GPT-3, again, the thing that kicked it all off, coincidentally had 300 billion parameters. This is completely independent from the size of the training data. GPT-4 is rumored to have 1.76 trillion parameters in total, but they're not. OpenAI is not very open about how it's built, unfortunately. And then Meta's Llama 2 model, the thing that was trained on 1.5 trillion words, the gambit that they were trying was, can we train a very small neural network on a large set of data and get a high-performing model? And they did. It works pretty good, not as good as GPT-4. You usually have to fine-tune it to make it particularly useful, but the important thing here is the scale. So the more parameters, the bigger the artificial brain, the better it is, but also the more VRAM you're going to need on those GPUs. So unless you're Microsoft, you're not running GPT-4. You have to have very high-performance data center-grade equipment to run GPT-4. I think GPT-3 is like 800 gigabytes of VRAM, so good luck buying that in 2023. Llama 2, though, you can run, and we have run, on this laptop. And Apple actually announced with the latest iPhone, they're using a transformer-based architecture to do next word prediction on your iPhone now. So that is very, very rapidly moving out of the data center onto edge devices. So as security folks, definitely worth paying attention to. Some of the things that a year ago everyone was thinking, yeah, if you don't work at OpenAI or Microsoft, you don't really need to worry about this. It's no longer the case as of February of this year. So we're going to look a little bit at fine-tuning and why we need to do that. So this is how something like ChatGPT is put together. So you take your user input, similar to the question we showed earlier, what's the capital of France, and set it up to where the assistant's going to answer. You shove that through GPT-4, and out comes the answer. The problem is, if this is all you do, it's going to keep asking itself more questions, predicting the next word, answering them until it runs out of space. So you have to do something called fine-tuning to get around this limitation. And what fine-tuning lets us do is train a smaller model that sits on top of the larger LLM that guides the output in a certain way. So instead of going on and asking the capital of Germany and so on, we can train it to emit, in this case, there's a special token in the vocabulary, or special word in the vocabulary to get it to stop. So we train that into the model. When you're doing fine-tuning, you can also train in all sorts of things. So if you want it to answer short and concise, you can show it a lot of examples of short and concise. And by a lot, I mean like 1,000. It doesn't take very much to train one of the fine-tunes. If you want it to have long, verbose answers, you show it that, it'll be long and verbose. So Mitch is going to talk about a research objective and some of the process now.
So in our research objective, one of the things we wanted to begin thinking about is what can language models learn. So how many folks in the room are concerned about something like ChatGPT, users in your organization using something like ChatGPT, and a risk of data loss? Fair show of hands. So our question that we wanted to look into is, can a language model memorize sensitive information when fine-tuned on user interactions? And so user interactions are just the prompts that users are putting into the system, into something like a ChatGPT, and the pair of the output of what the results were. So as Kyle mentioned, since OpenAI's training method isn't exactly known, we can't replicate it. But what we wanted to do to test this question was run a bunch of fine-tunes on an open source model that we could run locally and see if any memorization happens. One of the things that we have learned, the industry has learned, is that when you fine-tune models on good user interactions, again, the prompt and response pair, that it improves model performance. So for any of you that are looking at deploying language models or utilizing language models, this will be something that you may have to deal with. So now I want to walk through our methodology. How did we go about studying this problem? One of the things we did was we needed to have a data set that we could use, that we could trust would be a specific size, a specific scale, and that it met some certain requirements. We began searching for an open source data model that we could use, and we came up dry. So we determined we needed to create one of our own. And so we set out to create a data set that looked like a bunch of people from the same company talking about the same projects using something like ChatGPT to talk about sensitive information. Once we had that data set, we mixed it with a popular data set, an open source one that's optimized for chat. It's built and optimized to be better at chat responses. We call these mixtures between our data set and the chat data set a mixture ratio. And through this research, we did 26 different mixture ratios. And we did these different versions to measure the effects of if more or less information would be leaked, depending on the size and the amount of sensitive information included in the larger data set. So once we had those mixture ratios, we then ran those into the fine-tune training. We used the model we were using was Llama. And then finally, we did a model inversion attack, and we'll show in a little bit how that happened. So for our company, the company that we wanted to create these fictional business documents for, we created Purple Aerospace Manufacturing Corporation. We wanted it to be specific enough, but not that it would track to Boeing or Lockheed or anything like that. So in our the story that we've built up in our mind, the thing that we're working on, and we built into these prompts, is that Purple Aerospace is publicly known for manufacturing military and commercial aircraft. But they've recently been awarded a secret government contract to build highly invasive spy satellites. So the company is wanting to weigh the decision of, well, we want to leverage the latest technology in generative AI. We want to be able to stay ahead of our competition. There's a lot of features that we could implement within our programs by using generative AI and large language models. But we need to compare the difference between using something that, for our conversation, we're going to call public, something like ChatGPT, or private, running on your own infrastructure, something like a Llama 2. So for capabilities out of the box, ChatGPT is more capable. When we looked at those models a moment ago from Kyle, you saw how large something like GPT-4 is compared to something like Llama. So more capable out of the box. Llama is less capable, but when fine-tuned for your organization's needs, can deliver some specific value. Computing requirements. Kyle mentioned that GPT is running on huge data centers with tons of VRAM. It's really cost prohibitive, but for certain applications it makes sense. Whereas something like Llama 2 can be run locally within your own data center or even on something like a laptop. In terms of data residency, with ChatGPT, you're sending it out to a service like ChatGPT, and you're relying on them to protect your data, whereas something with a private model, you're able to keep that all in-house within your environment. And lastly, the pricing. With a system like ChatGPT, it's pay per use, so the more you use of it, the more you'll pay. It scales up as you're increasing your use of generative AI, whereas with Llama, it's a fixed cost. You're buying the hardware and the infrastructure up front, and then you realize the value over the life of that asset. So what they want to do is take the prompts that users are using. They're finding value in using ChatGPT today. Let's take that and leverage that for our business. So they're exporting those prompts out of ChatGPT and putting them into a data set, and then they fine-tune a private model based on that data. And then they run everything on Purple's private infrastructure. So now we're going to talk about synthetic data and how we got here. You can see in this flow chart, there's kind of three main areas. There's business documents, prompts, and then the synthetic data set that we end up with. So through our work, we created over 530 different types of synthetic business documents. And again, the important thing that we were going after is internal consistency. We wanted to have the same people assigned to a project be involved in the chats and emails that were related to that project. When we're looking at an org chart, it should make sense who's reporting to who. So some examples of documents we created were Slack transcripts, meeting summaries, project charters, things like that. How we did this, how we created these documents, was using the GPT-4 API with some code Kyle put together that allowed us to reference other documents as a part of our document generation process. So for building the meeting summary, we put a prompt into GPT-4 and said, your task is to write synthetic business documents for a fictional company, Purple Aerospace. Then we gave it some parameters. We said, you're a project manager working for this company. This is the level of detail that you should be thinking about. And then later down, we provide instructions in terms of referencing the top 10 projects the company's working on, the org chart that folks are aligned to. And then the output over here is a meeting summary that GPT-4 created. And so in here, it talks about tasks that were completed related to a milestone, tasks that are coming up, and open discussion items. So we take that meeting summary, and then we bring it over here. And so before, where it was us kind of generating the documents, now we would need to take the next step to begin building our data set that we're going to do our fine-tune on. So we took that meeting summary document, and now this is a user prompt with this draft email. And so this would be someone inside Purple Aerospace. They've got this document, a meeting summary, and they say, oh, I've got too much work to do. I need help. I've got to email a project sponsor, a summary of what we talked about. I need to fill them in on what we did. But I can't write it myself. I don't have enough time. So their prompt is to the GPT is your project manager working at Purple Aerospace. Reference things like the kickoff notes, the create task list, meeting summary, kickoff notes again, and create tasks. And so these the items that are in brackets are the variables that we're calling back. We're referencing as we're creating the documents, then later using as a part of building out the prompt and response pairs. So now we're going to take this prompt and bring it over here. And then this is the response that GPT created for the user within Purple Aerospace. So this is the gold that we need to build our data set. So before we were just generating documents. Now this component, these two items together, are the pair that allow us to build out our data set. So for prompts, we ran through a number of different prompts. I think there were more than 30 different types of prompts that we did. And so those would be things like format a press release, summarize test results, write application code. And so those took those business documents and then prompted them, and then we ended up with our data set. So now Kyle's going to talk about model training.
So we mixed up our data, so we ended up with 300 examples from those prompts that Mitch was just talking about. So we've got a Purple Aerospace employee and a pretty good response from ChatGPT coming back, and we want to make Llama a little bit more like ChatGPT. So we tried just our data, 0, so it's only the 300 rows that we made. And then we took a popular data set that folks use to take Llama and turn it into a, we have ChatGPT at home kind of thing. And here is a one-to-one, so it's 300 rows of our data, 300 rows of that tuning data. And we go all the way up to a pretty high ratio. So to visualize this, this is what 32:1 looks like. So there's our open source data set, and then there's ours. That doesn't look like a lot, so we kept going. We went as far as the open source data set would allow us. So there's the rest. So that's 115:1 right there, and that was the maximum ratio. And we actually had some interesting findings with that model that we'll see in here in a little bit. So each one of these we mixed up. We didn't necessarily train a model for every single one because there's some steps that aren't that interesting. We went from 0 to 1 to like 8 to 16, and then we were most interested in these kind of in the middle of the pack. So the training took a lot of effort, a lot of time over the summer. You can do this at home. It's only 11 to 16 gigs of VRAM to do fine tuning. You only need a couple hundred rows of data. It's not that big of a deal. However, we needed to do a lot of them. It was more than just the, I think we said 26 earlier. We ended up having to search for the optimal training parameters and work through some bugs in my code and the data set that we were using. So we did 182 total training runs over, I don't know, a 2-week period roughly. For the rest of the presentation, we're going to be focusing on 16 of them that we selected that seemed, the model worked very well, and it's something that a company might have actually deployed to production. The rest of them were us figuring it out. 824 hours of compute time consumed for training, and about $857 in cloud GPU use, and storage and whatnot. And we used RunPod for this. It's a pretty popular cloud GPU system. You can go in, put $20 on your account, and start training models this afternoon if you want to. So a model inversion attack is how we went probing here, and that's basically what everyone's afraid of people using ChatGPT over. If I type in sensitive things about my company into ChatGPT, can somebody else prompt it in a way that brings that information out later? And you might also use this, if someone has a proprietary model they've developed and you want to try to reverse engineer it, similar kind of thing. You're essentially trying to get bits and pieces or entire chunks of the original training set out so that you can replicate it or just know what was in it. So our prompts look like this to do the attack, and because we have control over the model, it's like in our scenario, imagine someone has broken into Purple Aerospace's network and they've taken their model file out. These fine tunes are only about 100 megabytes. It's a bin file of a bunch of floating point numbers. Doesn't really have much in there to tell you what's in it, so it'd be pretty easy for someone to get it out and run it locally. And when you have it local, you don't just prompt it and hope it works. You can go in and kind of put words in the response's mouth and corner it into a spot where it's either going to say, Laura Mitchell is a project manager at Purple Aerospace or something else. So we don't allow it to go on and talk about other things. We try to corner it and get it to either say the thing or not say the thing so that we can measure it. So out our 64-to-1 mix ratio, so kind of towards the middle of the pack, it guessed it. So that was about half that bucket filled with the tan blocks in one of ours. And it just came out and said it, Purple Aerospace, 72% probability on that. And then a couple of other words there were possible. And counterintuitively, a mix ratio where our data was a greater proportion of the overall, it was in second place, but it was behind the word a, or so maybe it was going to get there. But for our purposes, we didn't quite count that as a hit. We did measure those probabilities for 16 different models. So on this chart across the bottom, we have our mix ratios. So this is 8 parts open source chat tuning data set, 1 part ours, 48 parts chat tuning data set, 1 part ours, and so on. Up here on the left axis is the probability. So that is the percentage that the model assigned to purple, the word purple, regardless of where it was. In some cases, it was the 100th item on the list, and we had to go looking for it. The green dots is where it just came out and said it. And what's really interesting is it's not a straight line at all. It does generally decrease the more data you add, but we exhausted our open source data set that we had. By the final fine tune, it was something like 34,500 rows of the open source data set to 300 of ours, and it was still enough for it to know some things. So the problem doesn't necessarily go away. It does get a little bit better, but it is kind of lurking there. Another prompt that was very interesting, and this was our finding at the maximum mix ratio. So this is the bucket right now as it exists, our one little purple block in it, and it gave us 8 of the 10 projects that had to do with the satellite program. And it didn't get them all right, and it got some of the individual words wrong, but it got the gist right on about 8 of them.
In conclusion, going back to our research question that we started with, can a language model memorize sensitive information when fine-tuned on user interactions? Yeah, it can. If we jump back to what Kyle was just showing here, remember this is a part of a secret contract that only internal into the organization they should know, but somehow this ended up as a part of the the responses that we're able to pull out through model inversion. It would be a difficult situation for the folks in that company to have this model leaked or exfiltrated from their organization. So the takeaways, some of the things that we want to leave you all with that you can take back to your organizations when thinking about large language models and how to use something like generative AI. So the first one is AI governance is non-negotiable. One of the best things you can do with this is informing your users about how to responsibly use AI. So related to that, you want to inform them about the risks related to putting sensitive company information into the system and that it could be used later for training and then could be pulled out by an audience that isn't intended. Having strong communication with your employees around how to use it is important, but then also having guidelines and policies that support that. If your organization is considering using something like ChatGPT or other public AI tools, many of them, the enterprise grade ones, now have the ability to opt out of training. And so that's one of the easy things you can do, depending on the tool, whether you can do it at the enterprise level or the individual user, is to opt out of training. And that will help lessen the risk of your data being exposed. The next thing is, if you're going to fine-tune a model, you want to keep sensitive data out of that. And Kyle will discuss in just a moment a technique that you can use, such as retrieval augmented generation, on how you might work with sensitive information. You really want to protect your fine-tuned models like the crown jewels they are. In the exercise we ran through, the file ended up being about 90 megs. It has no headers. It's pretty innocuous. You might not detect it through traditional DLP filters. And then the last bit is you want to fully assess each version of a fine-tuned model for security and privacy issues. Each one of these fine-tunes behaved differently. So if someone comes to you and says, hey, I've got a model, and you go through and do a privacy review and you approve it, that's one set. But if someone comes back to you and says, hey, I've got a new model, I just upgraded it, does something new and different, you want to treat it as a net new item each time that you see a new fine-tune come through.
So earlier we had the Purple Aerospace generative AI implementation plan, and their plan was to basically just take everything down from ChatGPT and shove it into their model and call it a day. It's on premise, it's secure, right? But as we talked about, if someone gets that file, they've basically got a compressed representation that's really hard to detect of all of your secrets that are in there. So the right way to do this is you have your kind of standard LLM process here. When people are using it, you have your fine-tune there, you're collecting responses. The best thing you can do is collect feedback, what works, what doesn't, from your users. ChatGPT does this. If you look off to the right, you've got the thumbs up and thumbs down. However, what Purple didn't do is data prep. And you really want to do this. There's a couple of things you can do at this stage. One of them is detect and scrub out sensitive information. There's a lot of techniques to do this. There are some emerging techniques that have come out in the last year or two where you actually use an LLM to look for and replace and kind of Mad Lib out all of the details so that it's safe. So maybe that's something your model can do at night when your users aren't using it. You get your data set, you run your training, and do your fine-tune. So as security practitioners, you want to really focus on this data prep step and ask a lot of questions about what are you doing to make sure the details from these user interactions aren't going to make it through all the way. The other step where you're going to want to pay attention is the deployment of that fine-tune into production. And you probably want to have some automated evaluations and tests that look for this stuff and make sure there's nothing sensitive in there. If you looked at some of these prompts that we did, the model inversion attack prompts, if you go to a marketing conference or a non-security conference, people might look at that and say, oh, it's useful to be able to ask it what projects are we working on, right? And have that knowledge encoded in the model. You definitely do not want to try to train knowledge into the fine-tune about your organization because you have no control over who accesses it. There's not really a way to do access control at that point unless you're going to train a model for the CEO and a model for finance and a model for the intern. So if you just have one model that you're working with, you want to do a technique called retrieval augmentation, which is where you take your raw user prompt, hey, what projects are we working on? And then there's this thing called a vector database, and you do some AI math to figure out what parts of your organization's data are the most relevant to that user prompt, so like a list of projects from SharePoint or something. And then the retrieval augmentation tool goes and pulls that source data in as plain text and literally just pastes it underneath the user's prompt and passes that to the LLM. So this keeps the data itself out of the fine tune, but still lets you have those useful conversations and apply access control. And this is where scrubbing the data back out when you're fine tuning on the good responses that people got is paramount, because now you're putting it right in there. But this is probably the most sought after use case right now in people trying to run models on premise is how do I hook it up to my organization's knowledge and documents that we already have, because that makes it incredibly useful. So that's the end of our presentation. We have a little bit of time for Q&A. Would love to take questions about anything we talked about here or anything we didn't. So you're asking, like, how could somebody steal the model, basically? Yeah. Right, yeah. So you can allow people to use the chatbot without giving them the model file. They don't have, just because you can run it locally on your laptop, you probably shouldn't ship your model to everybody's laptop. You want to run it in one central place with access control. In our scenario, it's someone's broken into your network some other way and they see this 90 megabyte bin file sitting there and pull it out and start prompting it. So yeah, you can still make this useful. You do not deploy the model all the way down to the edge device at all. You want to keep that on infrastructure that is secured, requires extra steps to get access to, probably heavily monitored, much more than an endpoint device would be. Yeah, so there are some specialized models. So the question was, how do you do the filtering, basically, right? That step that we just talked about. There's been a huge surge in the open source LLM space since about February when Llama 1 came out from Meta. And a couple of the models that are out there are specifically tuned to just detect the presence of PII, like names, addresses, phone numbers, social security numbers, credit cards, whatever. So you can use a model like that to do the detection, and then it's some clever prompting to an LLM to replace it with something else. Because if you're trying to improve the model's performance, you want to actually show it an example of, hey, I'm trying to summarize this meeting. Here's a really good looking summary. We need to change enough details in there where the shape of the task is still preserved, but the details are different enough where no one's going to know what's going on if they steal it. So that would be like a data poisoning attack. So the question was, can you damage the model in some way to make it more susceptible to this kind of thing? It would be pretty difficult if just by sheer, let's say you had access to like the web UI of an organization's chatbot and you knew that they were going to even just like take everything that's happening there and fine tune on it. It'd be pretty difficult for you to prompt it in a way that causes more memorization to happen on all of the other things that it's seeing. When you're doing the training, without getting into too many details, it looks at those records as a batch. We did a batch of 8 records at a time. And then each batch of 8 is updating all of the numbers in that artificial brain a little bit, and then the next batch of 8 a little bit more. So there's not a lot of direct correlation or instruction going on there. All right, well, thank you so much, everybody. We have some links up here. So all of our work is actually open source. I'm not sure if the event is going to distribute this, but we'll have it out there on LinkedIn or somewhere you can find it. So there's a GitHub repo that has all of our data sets and links to all of the fine tunes themselves. We published them all on the Hugging Face Hub, all 100 and however many we ended up with. And then this code that I wrote called Tesseract is what we use to do the training, and that allows us to stack up a bunch of different training runs and let it run overnight, so I don't have to babysit it all the time. And then we also use that to probe the model and look at those probabilities and take it apart. So thank you, everybody.